Hello, everyone. Thanks for coming, and I'm very happy that you are here. I'm a computer science student at Warsaw University, and I will tell you something about the analogies in word2vec vector space. And first, a few questions. Who knows what word2vec is? Oh, that's great. Who doesn't know? And who's heard of it and didn't raise hand? Yeah. Okay. Yeah. Cool. And who's a word2vec specialist and knows everything about word2vec? Cool. That's great. Nobody. Okay. So basically, word2vec is the general idea behind word2vec is the distributional hypothesis. And it can be summed up to a word is characterized to the company it keeps, by the company it keeps. So what we mean is that when two words occur in the same context, almost always, they probably have the same meaning. Yeah, but it's a little bit controversial what we mean by meaning, but I won't delve into that. So we have probability that the word A appears in the context of a word C. So like I said, two words have similar meanings if they appear in the same context with the same probability. Yeah, okay, so that's great. We can tell if two words have the similar meaning. That's cool. But then to do that, we would have to know the probabilities for each pair, and that's quadratic memory, and we don't like that. That would be gigabytes of space. So what we do is we introduce something like pointwise mutual information, which basically tells us how much are the two words probable to occur together than if they were randomly occurring. And that's how much one word, appearance of one word tells us about the probability of appearance of the second word. And we want to approximate this PMI, and we do it by finding a vector for each word. Those vectors, we want to compute the PMI for two words, and what we do is we take the dot product of the two vectors, and thus we've got the PMI, but we've got to find those vectors, and that's when the word2vec magic happens. And that's a very deep topic, and I won't actually delve into how to find those vectors, but rather tell you about what we can do with those vectors. Yep. Is it better? Yeah, can you hear me? Yeah, cool. Okay, so we've got let's imagine we find those vectors. We found the vectors, that's cool, but yeah, do the vector similarity mean that the words are similar? We're not so sure. So we want to actually check it. We've got the equality of the probabilities for each pair, for every word, and then dividing by the probability of word C appearing and taking the logarithm, we've got the equality of the PMIs. We approximated the PMIs by the vector dot product, and now taking to the other side, So if it has to hold for every word C, then we've got an equivalence in the vectors. Yeah, okay, so now we have a tool to measure how much similar are the words, and that's cosine distance. So we already know that similar words have similar vector values, and now we can use the cosine distance to check to find the most similar words. Yeah, and sorry about that square on the edge. I don't know why it appeared. Yeah, but we want to find the most similar words to blue, and actually the model, yeah, finds them. Those vectors here are from Glove implementation. Yeah, they are trained on Wikipedia and GigaWord 5, I think. Yeah, okay, so we can see that word2vec captures different types of similarities. Yeah, even if we take some Renaissance painters, actually the most similar are other Renaissance painters. Yeah, it can generalize Europe. There is world and continent there, and there are other forms of the word stance. So okay, it's pretty intelligent, but we're not so impressed yet, right? Yeah, okay. And who's ever heard the king minus man plus woman equals queen? Yeah, okay, that's cool. So that's what this is about. Our model is capable of solving those analogy riddles. And we want to find the vector which is the answer is the one which has this value the highest. So we're looking for such VB that this is the highest. But what it actually means is that we're looking for vector VB which has the maximum dot product with Vy and Vx. But also at the same time we're minimizing the dot product with VA. Yeah, so we actually now it can do things like tell us the capitals of the tell us what country the capital is in. It can find us the antonyms. Yeah, I think this one is pretty nice. That hope is to disappointment as peace is to disagreement. And also on a little bit more generalized level, we can find that a country is to language as Britain is to English. Well, that's nice that it's working. But I also a little disclaimer. I picked those examples, so it doesn't work always. But I was able to find them, right? So yeah, I was surprised by this one that it actually worked. It was pretty nice. Yeah, but we can ask also word2vec for its so-called opinions, and actually it thinks that Henri Matisse is the Einstein of painting, and also that Nietzsche is the Copernicus of philosophy. So maybe in an alternate world we would be sitting in a Nietzsche philosophy center. Yeah, but okay, so the analogies are cool. Some word2vec models can solve them better than an average American high schooler. And yeah, what more can we do? We can take a word and measure its association with measure whether it's associated more with one word or the other. So, for example, we can measure. We can find the gender of a name. we can we can find out if the words are positive or negative. And for that, I wanted to show you an interactive visualization, which I did under the mentorship of Piotr Migdał, who's sitting here. Yep. Yeah. So actually, we can see that that the male forms are much closer to he than she. And actually, wow, that's cool. Actually, because we didn't tell the model the concept of gender. And now we can. Yep. Also, it works with it. It's not so clear here, but it works with grammatical forms. So we can see that the adjectives, align about around that V. But what I also wanted to show you are the jobs. Okay, so in the corpus, which this model was trained on, there was actually some gender bias, and so so CEO is like, well, it's much closer to he than she. That's surprising, isn't it? Yeah. So we've got actor and actress. It's actually aligned well, and plumber that's rather male, and the nanny is rather female. Yeah, we don't like that, but I will talk about that in a minute. Yep, and I wanted to invite you to play around with that, because I think that's the most interesting part, that you can actually type in and see what's gonna come up. Also, the other interesting thing is that I don't know if you heard of it, but there is something like conceptual metaphors, which are so natural in our language that we are not really aware of them. And when we visualize the vectors, they kind of show up. Yeah, for example, conscious. When we say someone is up, they're not sleeping, they're conscious, and actually it has a lot on the. It is much more associated with up than down. Yeah, but similarly with rich and poor, and probably important and unimportant. I think that's pretty nice that it shows here, because it's something that people are not really aware of. Yep. Okay, so now imagine that you are a geologist. So you like the earth and rocks, and you've recently been interested in data science. Someone told you about word2vec, and you just, oh, what's that? So you want to, so I will order it to find the words most similar to rock. But as you can see, that's a little bit disappointing, because people would rather listen to music than talk about stone. So what you do is you project the rock vector on music vector and subtract it from the rock vector. Yes, so what it gives us is the vector that vector rock is perpendicular to the second vector. That's cool, and it actually gives us good words, which are all are associated with the actual stone and rocks. Maybe this one isn't, but it's a spin-off of the Muppets. Yeah, it was called Fraggle Rock. Yeah, okay, so now you're a data scientist and you want to find the most similar words to Python, and suddenly, yeah, it's Monty Python and Spamalot and John Cleese. So you take away Monty, and oh, whoa, it's actually working. Yeah, but you don't like that it's PHP here, so you take that away, and you're left with the animal. And that's a little bit sad for you, but you still continue on to be a data scientist. Yeah, also, we've got our Polish language, and the most similar vector to it is Lithuanian. Yeah, and that's cool. That's okay. Lithuania is near. We take away Lithuanian, and we get actually the Polish things. Yeah, Wałęsa and Pope, and yeah, and German. Yep. Okay. So the next thing that we can do, going back to the gender bias, is that we can take all of the vectors and reject the gender for it. So we reject the she minus he from all of the vectors. So if on normal vectors we would take genital, so the most similar are female names. And now when we take away the gender, what we get are the names of different genders, which are all, well, I guess they are kind of the same, maybe given in the same time. And similarly with mother, because the most similar vectors to mother are daughter, wife, and grandmother. Yeah, and then there's husband. But actually, well, actually, if you ask for the most similar thing to mother, it should be father, right? Because the father has the similar role, and yeah, if we take away the gender, what we get is the closest one is father. Okay, so actually, this gender bias in the word2vec model can bring us some problems, because there are some studies about developing a word2vec a search engine which is helped by word2vec, which positions the search results based on the association with words, and that would be kind of bad, probably, for example, for female programmers, because he is more associated with programming than she, and that could bring the male programmers up and the female programmers down. So I read this study, and there's a way to get rid of that, which is kind of successful. That they take the Amazon Cloud tethers, it's called like that. So they crowdsource the analogies, and people rate whether they are gender biased or not. So, like CEO versus housewife, it is gender biased, but for example, sausage versus buns, it's not gender biased. Yep. So actually, having data like this, you can make a transformation matrix, which allows you to take away the gender bias, and the words are then much less biased, and it's a kind of a solution for this problem. Yeah, so vectors are generally of different qualities. There are some analogies can be found in some models and some not. So there are three most important things. that contribute to the vector quality. The most important, corpus size, it's typically a few billion tokens. The data that I used here was trained on 6 billion tokens, and there were 50 dimensions. But they were cut. I had to cut down to the most frequent words because my laptop wasn't kind of coping. And also vector dimensions are very important. For some tasks, vector dimensions like 1,000 are better, but for some that it's found that smaller are better. And the one explanation of this phenomenon is that probably the less dimensions makes the model find different abstractions and relations, which allow it to incorporate the analogies better. And also the vector deriving algorithm, that is also very important, but that's something which is, well, that's a subject for another talk and probably another 50 talks, because there are many of them. Yeah, okay, so that's all from my side, and thank you a lot. You can find me on GitHub. You can find this visualization, and I invite you to play around with it. Yeah, thanks. That's all from me.
Okay, so do we have any questions? Oh, so many questions. Let's maybe start.
I have a question regarding this projection to two-dimensional space. So could you explain maybe how did you make these words projected to he or she or good, bad vectors?
Sure. So we're talking about this, right? And where this comes from. Okay, so the first coordinate is the dot product of. Let's say we want to find a place for the word quiet. So the first coordinate is the dot product of the vector quiet and the difference of good and bad. And the second coordinate is the dot product of the vector quiet and the difference between down and up. Yeah, like it's like here. Yeah, cool.
Thanks for the presentation. My question is how much data transformation in terms of lemmatization and stemming is required to use this approach? And maybe as an extension, can this library methodology be used to boost or replace current lemmatizers?
Well, generally what I did here is I downloaded the vectors from the Glove site, which you all can do, and I just used them as they were. So I didn't have to do any processing to them, and I'm not really sure about what the question is about. That's probably my fault, but I guess I can find out and contact you later.
Okay, so another question?
Did you do any hyperparameter tuning? I consider vector size or dimension the hyperparameter of the word2vec. And did you see any changes in the results or not?
Well, I tried out a bigger data set, vectors trained on with many more dimensions, and the analogies were better.
Better?
Yeah.
In that case?
Yeah, in that case. I also checked out different publications which were comparing different architectures and the size of the corpus and the length of the vectors, and generally the bigger is better, right?
Okay. And the corpus was downloaded from what? Where?
Yep. In the description on the PyData site, there's a link, but it was downloaded from. Yeah, that's from here. You can download different versions here. Yeah, I took this one. And for the visualization here, it has to work locally because it's written in JavaScript. So actually, it's the 100,000 most frequent words, and the numbers in the vectors are cut down to 3 places after the comma because it had to be small enough so people could go there and download it. So here are not the best vectors, but the best I could do.
Did you try to? Could you go to the example when you were subtracting the music aspect of
Yeah, sure.
rack? I mean, in the code. In the code. Next one.
Yeah.
Yeah, right. So did you try to subtract more than music? Because what are you doing is subtracting the aspect of music, so projecting on an orthogonal completion of the music, so you could did you try to find the subspace that corresponds to music, or did you just do this one? I mean, for music, the subspace corresponding to music should contain classical piano or something like this.
Yeah, I get what you mean. That's I probably could have subtracted music and piano and pop, for example. But actually, if you subtract too much, it gets they just you get some trash from the. Yeah, probably if I tried to subtract piano, etc. It might have been better, but I didn't try it. Yep. And
Then there is a location of representing stuff in word2vec with lower dimensional subspaces. So doing PC, taking music, piano, classical, I don't know, hip hop, and then getting PCA, not just the span.
yeah, probably you could do that, but I didn't try it out. Yeah, I can publish the notebooks online if you wanted to try it out. Yeah. So you mean? Yeah, with word2vec, it's kind of if you have Polish is a fractional language, so we don't have rock in Polish is skała, but it's also skały, skale, skałom. So you've got different endings, and word2vec isn't as effective for fractional languages, so it wouldn't be quite impressive. Yeah, but there is research going on regarding taking the n-gram parts of words and then applying it to the vector generation. But I don't know how it's doing for Polish, because they did it for English in the publication, and I think that's not nice.
Someone else? Okay, I think it would be the last question.
I was just wondering, would word2vec be useful for creating a sentiment analysis tool, like Twitter?
Well, you could probably find well.
If
You
not,
could-
what would you recommend?
Sorry?
If not, what would you recommend instead?
For creating sentiment analysis?
Yes.
Well, I think that for creating sentiment analysis, word2vec wouldn't be so useful because for word2vec it is also important what parts of the sentence are the words. So good, and it's also not good with telling apart antonyms. Yeah, a few slides. I've got, yeah, I didn't put it here, but you can see that if we take, if you want to find good is to bad as apt is to, the second thing is up, because actually antonyms also find themselves in the similar context. So you can probably say that the food in the restaurant is cheap, but you could also say in the similar context that the food in the restaurant is expensive. So that's, I don't think that it would have very good application here.
Thank you.
Okay, so if anyone has another question, so I think you can find Julia on the coffee break.
Yeah, thanks.
Thank you very much.